All right, so we're very lucky to have Chris Malone here. So he's a world leader in data center networks. I'll let you get set up here. He leads the data center hardware at Meta. Prior to that, he was at Google, where he developed next generation technologies for all aspects of the Google data center infrastructure. And he's led the invention and delivery of multiple generations of Google data center architectures and technologies around the world. And he has over 100 patents. And his colleague is here, Catherine Schmidtke. I don't see her at the moment. There she is. But she's been a leader of our interactions with Meta over the last 5 years, and also an expert in data centers. So with that, Chris.
How's that? All right. Well, thank you for inviting me here today, John. Really appreciate it. And it feels like you were kind of a lead into this presentation I'm going to give today, because there's a lot of commonalities, which is nice to hear. Perfect. Thank you. So my name's Chris Malone. I've been at Meta for three or so years. Before that, I was at Google for quite some time. So I've been working in the energy efficiency space for compute and data centers for almost 20 years. So it's really fun to be here today and talk about efficiency, and kind of have a hint there that when we're thinking about data centers and hardware, we think about energy efficiency, of course, but there's other aspects to this too, like water efficiency and how we think about carbon, and all those things are really impacting our data center design these days. So my responsibilities, as John said, are to kind of lead the technology strategy for our data center world. I work really closely with folks across the hardware and software space to kind of come up with an integrated co-design, if you will, across that entire stack. One sec. Okay, so I don't have very much time today, so I'm going to kind of breeze through these slides. Just to give you kind of some grounding in terms of data centers, 10, 20 years ago, nobody knew what a data center was, including myself. And now it seems like it's in the papers all the time. But just to give you a sense of this is one of our data centers in Ireland. And one of the things that's kind of striking for me is, in order to get the whole complex in the frame, you have to use a helicopter or a drone, right? These things are so big that they take, quite some time, an hour to walk around the facilities or more. They take billions of dollars to erect, right? The CapEx is all upfront loaded. They take 2 to 4 years to build out, sometimes more. And it involves thousands of people working on site. So it's a labor-intensive effort, and it's sort of built for permanence. The infrastructure that goes in it amortizes over 10, 20, 15 years. So this is the dilemma, that hardware and software change at a much different rate. So one of the challenges here is, like, how do you balance those two things out? This expensive upfront asset that's going to be loaded up with this equipment that actually ends up costing a lot more over time. So to me, like, this is what's kind of interesting about data centers. They're sort of the crossroads of so many things, right? From policy and land acquisition and energy grid, to the hardware and software that goes into it, the networking as well, of course. And it's sort of this compromise of a bunch of different things that go in it. So I've been lucky to have been part of the hyperscale world pretty much from its beginning, and seeing the emergence of these large-scale data centers around the world. And as I said, like, one of the challenges is, like, how do you strike the right balance in terms of designing for something now that'll show up in a couple years, and we don't really know what the hardware world will look like then. And what's interesting is, I would have said that throughout my career, but it's even more so now, right? Like, AI is really throwing things for a loop, and I think that'll become clear in the following slides. But just to give you some brief stats on the business side, so Meta stats from the latest earnings call. One thing that I kind of forget this, but across our 4 big services, about half the world touches it at least once a month. So in order to support something like that, we've built out a global computer, I would say. So like that's how I kind of think about it. For the last 13 years, we've been designing and building out these facilities in North America, Europe, and Asia to serve this need. And interestingly, this design that was created back in 2009, 2010 hasn't really changed all that much because, if you abstract a bit, compute hasn't changed all that much in the last decade or so until the emergence of AI. So just before I move on, it's more than just those buildings. There's the global computer. So we've had to build out undersea cable, fiber across Pacific, across the Atlantic, and then terrestrial networks in the EU and North America. And when this first started rolling out, where the hyperscalers were doing this, it was like front page news. It was a big deal. Now I kind of had to, when putting this slide together, it's like, oh yeah, we do this all the time. And all the hyperscalers do it. So this is kind of like one of the consequences of building at scale, and it certainly helps with efficiency to be able to, distribute your workload appropriately. So just a little history before I get into the impact of AI on compute and data centers. There are two metrics that we use as an industry to sort of make sense of energy and water efficiency. And as John referenced, the nexus of energy and water, they're all connected, right? PUE is the first one, and this is a metric that kind of introduced me to the efficiency world. A colleague and I proposed this in a paper back in 2006, and it measures the total amount of power going into a data center divided by the IT power. So anything above 1 is waste, or essentially the burden of mechanical power and cooling power to make the IT run. So you want the number to be as close to 1 as possible. And so introducing that metric actually had a really profound effect on the focus on energy efficiency across that whole stack. And at the same time, the emergence of hyperscalers actually made it quite easy. So we have full visibility into the cost and efficiency at all the layers, and it hits our bottom line. So it was the strong motive to fix this. And so we've seen, what used to be a PUE of 2 not that long ago is now 1.5-ish or so. And we've been hovering in the 1.1 range for the last 5 or 6 years. Similar results from the other hyperscalers. In terms of water efficiency, there's another kind of analogous metric that looks at the amount of water you use, and you can see that the Meta data centers perform very well compared to those metrics. So these are hugely important for us in terms of our efficiency effort. So that's kind of why I say it's energy efficiency, but it's also some other things. So here, in the interest of time, I'm just going to click by 2 of the major factors behind energy efficiency at the data center level. So first is the power distribution. And I would say this is mostly a solved problem if you control your whole stack. So on the left is like how you get power from the grid down to your server. And if you don't build your own stuff and you go to a colo, your losses might be in this range. You might be on the 10% range now if you're really paying attention. Could be higher. If you can design the whole stack, you minimize the number of transformations and you gain some efficiency right off the bat. So this is what we've been doing for a decade or more. And it's, we get incremental performance improvements over time, but mostly on the server side at this point. One other brief point, one of the luxuries of owning the whole infrastructure stack is we can make intelligent decisions about things like backup. So every data center in the world, mostly, has a diesel generator backing it up just in case. So we design our infrastructure with from transmission grid power, highly available, multiple feeds and so on. So we're able to make calculated decisions about we actually don't need these generators because the probabilities of failure are acceptably low and will fail over to another site if that actually happens. So that helps us in terms of carbon and CapEx and all kinds of beneficial things. This is really difficult to do if you don't own that infrastructure. The other part of the data center efficiency term, and probably the dominant one, is cooling. And so without going into the gory details on this cooling system, it's essentially the same as using this building. You kind of open the window and use outside air. You pull it in. It's a little more complicated. You need to condition it when exactly you need it with some evaporative media, but this is pretty critical to achieving exceptionally good efficiency at the data center level. So typically, like, cooling represents 2/3 of that overhead, 1/3 for electrical. So being really mindful of the cooling part matters a lot. And that is actually a challenge when we talk about AI. So hey, everybody that's been paying attention for the last couple of years knows that AI is affecting us in a societal fashion, but this group is pretty aware how much it impacts everything in the software, hardware, data center world. So just for a brief kind of perspective, and John showed some graphs here earlier on the size of training models, but this is our recommendation model, deep learning recommendation model from 2022, not that long ago. And this was our focus in 2022 was, how do we do training for recommendations and surface the most useful information? Tough problem, but we were working on that. But the emergence of Gen AI, and very late in 2022, early in 23, kind of took that work that's been amongst the experts in AI, has been cooking for a long time, but made it prime time. So for example, the Llama model with 65 billion parameters came out in early 23, and there's been iterations since then. But what's instructive for the compute data center side of the fence is the consequences of the scale. We talked about a few years ago about data center scale training as a special case. Now it's a prime time case. So you can see here some metrics: a 400x increase in compute, 10x increase in memory, 20x increase in the training size. And the thing that makes it interesting is we don't actually know where this is going to end, right? So we still see improvements as the training models get larger and more sophisticated. And so we'll continue to push on this. And so this is where it's very important for us to be mindful of the efficiency aspect of these things, so we're not chasing pure performance, right? So there's a lot more to say on that topic, but I think this audience is pretty clued into it. But it brings us to this kind of transition point that I helped lead over the last few years, where we had this amazing data center, stable performance, leadership, and a bunch of efficiency metrics for years, and we needed to change. And the change is driven primarily by power and cooling. So things that we had relatively under control. Here's some facts, right? So the rack power, average rack max power per rack is projected to be 10x what we used a few years ago in our old data center. 10x increase in the chip power. And that drives us to liquid cooling. And there's a bunch of other attributes that are unique that I'll just briefly touch on. So I think for this audience, this is insultingly low level, but just to kind of ground everybody, training is basically like building a giant HPC machine. So they're highly interconnected racks and chips. We have, in our case, what we call a backend network, which is low latency, non-blocking across many, many thousands of chips. So proximity of racks to one another, proximity of chips matters in a way that it's never mattered before. Like, we used to have a scale-out problem that we could shard everything, and it wasn't as the benefits of cramming things together just really weren't there. So each one of those green circles represents an AI rack, and each one of those has 16 GPUs. That's sort of what we're doing today. But the 2x factor is a real thing, so we could imagine that doubling and changing in many different dimensions. So here's kind of where, breaking it down visually, this is the GPU server that we're kind of introducing today with 8 GPUs per chassis. But the real action is here. This is the typical 2.5D chip package for AI. And so without getting into the details about what that means, it's just a whole bunch of compute crammed onto a silicon substrate. You have things that cause tremendous issues with cooling, like stacking of active memory chips and so on. But again, I'll fast forward. Here's where it's going in terms of power. So not that long ago, it was in the 400-ish range, and our typical server power was much, much lower than that. Like, we weren't pursuing the max power CPUs for performance reasons. That's kind of changed here. So we're at 700-ish watts right now, and we're right on the limit with the next generation of going to liquid cooling and needing it for performance and meeting the thermal requirements of the chips. So in the not too distant future, over the next couple of years, we see the numbers approaching 1,400, and there's error bars, because if you look out to 2029, a lot of these fab processes haven't been developed. We haven't thought about the packaging work around it, so the error bars are substantial. So we're preparing for that with this new data center design, but in short, we needed to basically develop, among other things, a new cooling system. And this is where the efficiency topic is important. So with the old system, we used outside air. It was wonderful. With liquid cooling, you need to pump the fluid to the chip. So that requires a whole new design. And so this is kind of what it looks like. And without going into much detail, it's like you have a heat exchange between water that goes to the ambient and water that goes to the chip. And here's where the efficiency matters. So this plots the amount of power we use over the course of the year for chillers as a function of location. And location represents cold on the left to hot on the right. So the message here is like, hey, if you're picking a coolant temperature, the temperature that touches the chip, that's too low, then you're going to be running your chillers all the time. And you can see that in the top blue line, it caps out. So like half the world, you need to run the chillers all the time, basically. And so we've been working with a number of industry partners and our peers to hone in on what actually makes sense, like balancing the risk of the unknowns in terms of chips with a goal of being as energy efficient as possible. And we landed on 30C as this number. And the number is not important in the abstract, but this is sort of a balancing act. It's what we use for air cooling, and air cooling is not going away anytime soon in the data center. And this kind of liquid cooling temperature matches well. So no real changes, and you can see the partners we've kind of aligned around this. And this is certainly not without risk. It's going to demand a lot of work on the chip packaging side to manage that risk over time. So this is a brand new topic over the last few years. So just briefly on sustainability, this is another huge topic for us, of course, and personally very important to me. I want to focus on water to kind of close out here. But we have like three major things, right? So net zero, our goal is by 2030 to be net zero across scopes 1, 2, and 3. Scopes 1 and 2 are easy-ish. We've been net zero on scope 1 and 2 for the last few years. Scope 3 is the big target that we're working on as for Meta, but also across the industry. We've been 100% renewable energy for our data centers and our offices since 2020. And then finally, there's a goal that's sort of surfaced over the last few years as a real thing. It's water positivity. So by 2030, we're going to return more water than we consume to the world across the whole company. So 5 years ago, water was not really talked about broadly in the data center world, partly because it's where data centers mostly located. It was cheap and plentiful, but that's obviously changing quite a bit. So the issue here that we need to work on as an industry is on the heat rejection side of this cooling schematic that I'm showing here. So we, as a company, are very much embracing like a waterless data center. It's kind of odd. I'm talking about liquid cooling, but also waterless data center. So waterless meaning no water, no phase change to remove heat from the data center. So it's all driven by air cooling, basically. The problem here is, like, if you look at that PUE efficiency metric on the vertical and water consumption on the horizontal, WUE, this is where we are operating today with our data centers. So very good results in terms of both, as I showed you. The problem is the conventional solutions that support liquid cooling at scale don't really do a great job of that balancing act. And as an industry, this is what we need. So there's 3 that I point out here that you can basically go and buy and without a lot of thought. Dry coolers means it's basically a giant heat sink that sits on the roof of a building or somewhere, and fans blow air across it, and hot fluid comes from the data center, and that's how heat is removed. And if you look at your local supermarket, they've got one on the roof too. And it's not great from an energy efficiency perspective, but it's amazing in terms of water consumption. On the other end of the spectrum is evaporative towers, and if you may have seen pictures in the media of data centers, and you just show this big plume of evaporating water, and that's what that is. And it's amazingly economical, it's great PUE results, but it's really sort of out of step with time right now. Like, it's really not the solution that this industry wants to deploy. And then we have a tweener solution that has all kinds of issues in terms of cost, complexity, so there's nothing great. So as an industry, one of the things we've been focused on is how do we get back down to this level of PUE, WE performance. So that's something we're actively working on. So how are we doing on time? Got it. So just to recap, we've got this brand new data center architecture, which we absolutely did not want to build. Like, we do not want to do liquid cooling. It's driven by this profound technology transformation that makes so much sense from so many different angles. And it's very exciting as a technologist. But what is true is our commitment to this power and water efficiency. And also the efficiency around carbon, which I won't talk about today, but that strongly influences how we design hardware and data centers. And then I just pointed out a couple of things that the industry needs to maintain all the efficiency gains that we've achieved over the last 15 years. So with that, I'm going to conclude. Do we have time for questions? Or? Yeah.
All right, again, for everyone in the back, there's more chairs up here, so come on down. So,
okay, yeah.
Any questions for Chris? Yeah. Rich.
Thanks for the great talk. How do you sort of balance carbon efficiency versus energy efficiency?
Yeah.
Less energy efficient, but a lot more carbon efficient, and would that be good?
Yeah, that's not a simple question, right? There's actually not a lot of great answers to the carbon problem. So there's a couple that are obvious. One I mentioned was taking generation, fossil fuel-based generation out. And that's an industry challenge. It's very difficult. There's green concrete, and there's lots of motion towards doing that. We've aligned with our hyperscale peers on kind of making that a thing. And there's obviously decarbonizing steel and other parts of the ecosystem as well that we're looking at. But one of the advantages of AI is we have this density, right? So it means pouring less concrete, putting in less steel. So there is some upsides to that we're taking advantage of. Yeah. Yes.
While Chris asks, Eric, why don't you set up your computer? Oh, there you are. Sorry.
Two questions. Quick one. I noticed you're using Google Earth. Are you allowed to have a Google name on Meta?
Maybe I get a free pass because I used to work there. So.
I have a question for you on the liquid cooling.
Yeah.
So clearly you're doing it because you want higher energy, power density.
We're doing it because we have to, because the performance requirements require that transition to liquid. Yeah.
Right. So my question is, couldn't you use optics to separate?
Yeah.
Compute, and then you wouldn't have to go to liquid?
Well, maybe. I mean, this is interesting. Like, as an industry, we've been talking about, disaggregating compute, onboard optics, and we've been talking about all kinds of exotic cooling with 3D packaging for 20 plus years. So there's lots of ideas waiting for an opportunity. So I think you're going to see a lot of evolution of the underlying hardware architecture over the next number of years, driven by demand. Right? Yes, sir.
Who actually, energy without fire, who actually pays for the cost of the vastly expanded AI architecture, or do you figure you're just going to make that
Oh, yeah. Well, thankfully that's not my department. But well, I mean, I think it's very much an open discussion right now. It's like there's been lots of news about how Gen AI cost per transaction is X, and it needs to be X divided by 10. So it's a huge focus. Obviously, these are commercial companies, and there has to be a rationalization period. But right now, there's a lot of discovery happening. Yeah.
Great.
Yeah.
Are you ready? Okay, go ahead, Mark.
One of the places I didn't hear you say that you're spending a lot of energy,
So to speak. Yeah.
is to convince certain hardware like NVIDIA to dramatically improve their, the energy efficiency of their machines, of their
Yeah.
chips and stuff.
Yeah.
And I saw there was some in that discussion, but can you talk?
Yeah, that's a great one. So absolutely, that is kind of intrinsic to that kind of nerdy looking topic of 30C. It's forcing a conversation around the balancing act, because if you weren't constrained by energy or cost, you would build a data center, a cryogenic data center, and then you would never have any problems, right? That makes no sense. So left to our own devices, we would optimize for performance in the abstract, especially since nobody really knows where this field is going. So this effort to harmonize around a common, reasonable temperature that matches the efficiencies we've already gained is kind of a part of that strategy. Like, we can't just go open loop on performance and future-proofing against all potential outcomes. Yeah.
All right. Thank you, Chris.
Okay. Thank you.